Okay, so this is actually work that has been ongoing for a long time. I've been carrying out this work alongside Chris Partridge, who's the next speaker, and it's actually inspired by work that he started doing. I won't say when, because maybe he doesn't want me to. It's based on several publications that we've published over the years, along with Chris and also Andy Mitchell, who's here as well. And the title of the talk is Ontology-Driven Conceptual Modeling. And during the presentation, I will explain what all these terms mean, although I think ontology is becoming more and more mainstream, especially with artificial intelligence and given the deficiencies such as hallucinations of current AI systems. And specifically, I'm going to talk about a specific approach to doing ontology-driven conceptual modeling, which is known as 4D, or more precisely, a 4D extensionalist approach. So the talk will have these, we'll discuss these different areas. So I'm going to talk about initially the problem. So why do we need 4D extensionalist ontologies? Define conceptual modeling, because it is actually one of the main branches of computing and information systems. But I think many people don't actually know exactly what conceptual modeling is. And maybe I would say that even the conceptual modelers don't know exactly what conceptual modeling is. Then we'll look at ontology. And ontology is a term that's widely used both in philosophy, where it originated, but also in computer science. And some of you may have heard of the semantic web, and that's where they do speak about ontology. So there are two different perspectives on ontology, if you like. There's the philosophical perspective, the computational perspective. But in, let's say, for practical work, sometimes these two need to come together, and I'll explain a bit more about that. If we use a philosophical stance, what is important are these, what we call metaphysical choices, so the theories that need to underpin what we do. And then I'll show some examples from our work, the work that we've done in the past. They're actually simple examples about how to model with different metaphysical choices, and then an example, if I have time to go through it all, about how to use 4D ontology to improve legacy data, so data of legacy systems. And then I'll draw some conclusions in the end. Okay, so I'll start off with a question. So if you have a look at this map and you ignore, let's ignore Ireland, because I couldn't delete it from here. How many countries do you think there are? Four countries. Okay, any other answers? So the thing about the United Kingdom is that there is a country called the United Kingdom, but it also has four so-called home countries, which are England, Wales, Northern Ireland, and Scotland. And depending on the classification of countries that you use, you can consider England, Wales, Northern Ireland, and Scotland as countries. Or you may just consider the United Kingdom as countries, but sometimes you actually need to consider both classifications at the same time. Because there are, when we design and develop information systems, there are problems that can arise. Actually, you may not think of these as problems when you go and buy something in a shop, but they are actually problems. So what happens if a product is sold in Scotland? Is it also sold in the UK? We would say, yes, it is, because Scotland is a part of the UK. What if this happens? So in 2016, Scotland had a referendum to leave the United Kingdom. They voted no. But what happens if Scotland or another home country leaves the United Kingdom? If we make a sale, then does that, the product being sold, is it sold both in Scotland and the United Kingdom? Well, if Scotland leaves the United Kingdom, then the answer is no. But then does that apply to the past Scotland? And is the past Scotland the same as the current Scotland? Okay, so you have all these interesting questions, which underlies the importance of what this talk is about so-called ontology, but also semantics. So these questions exemplify difficult problems that are inherent in the development and integration of information systems. So a simple example like countries actually exhibits complex problems that need to be designed into the information system. So let's look at conceptual modeling. So first of all, a model can be defined as a representation of something. So for example, if you have a blueprint of a building, that's a model because it represents the building. If you have a train schedule represents the running of the train. So the train schedule and the blueprint are both models, and we can call them conceptual models. So models underpin all aspects of information systems development or engineering. And to take it further, although this talk is not about artificial intelligence, models also underpin or should underpin the knowledge of AI systems today. And that's currently what generative AI systems don't do. Okay, I won't go into the details, but that's not what they do. And that's why we have some of the problems we have. So these are two definitions that we find in the conceptual modeling literature. And they're quite dated, but they're still currently used. So if you go to the International Conference on Conceptual Modeling and they define conceptual modeling, the Mulopoulos definition is one that's widely cited. Now, if we look at it, I've highlighted in red the main aspects. So there's representation, and I've spoken about representation, representing both the physical and the social world. So not just rocks and mountains, something that's physical, but also social constructs, socially constructed things like money, government, marriage, and so on. And in business, almost anything we talk about is socially constructed. Now, we'll see later that in a 4D ontology perspective, even the social things are physical. Okay, and I'll talk a little bit about that later. Now, are these definitions appropriate for the current context of information systems development and integration? Well, we would say that they're actually quite dated because systems today are in a continuous state of flux. There are always new requirements. So imagine if Scotland left the UK, that's a requirement that we need to take care of. And if our data structures underpinning our information systems aren't able to cope with that change, then the change can happen, but it will be very costly and more difficult to do. Another thing is that in the past, there wasn't much machine-to-machine interaction, automated connections between machines, so machines talking to one another. Now we have interconnected machines that need to pass data from one another in an automated manner. So it's the problem with data integration and data interoperability. So while the definition here talks about learning and problem solving among human users, nowadays we have this extra complication whereby machines need to communicate with one another in an automated fashion. Okay, so hopefully the message I'll get across today is that 4D ontology will help in this sense, and we'll take conceptual modeling further into what we can call maybe 4D ontology-driven conceptual modeling. So this is the data integration problem. So many of you may already be familiar with this. So we have structured data sets such as things represented as tables. And we have unstructured data sets such as emails, so documents in natural language. Obviously, managing unstructured data sets is more difficult than managing structured data. But here, the whole essence of the problem is that we want to take heterogeneous data sets, and bring them together so that they are semantically consistent, so that they're able to represent the domain of discourse for the real world in a consistent manner. So why do we need this? Because the challenge is that we have increasing amounts of data out there, whether they're publicly available or you can acquire them privately. But even if you don't acquire external data, if you take a large multinational organization, it already has probably, petabytes or exabytes of data that needs to be managed. For unstructured data, as I said, the problem is significantly more difficult. And in the examples that I'll show, we're starting from structured data. Okay, so think about tables in a CSV file, in a spreadsheet, and so on. So at the very beginning here, I talk about syntactic formats. So you're familiar with many of these. And although that is a problem, that you have different formats, that's not the main issue. So syntax is not the main problem when talking about data integration. Semantics is. Just one word on AI. All of us have used Gen AI systems such as ChatGPT. And one can say, well, why don't you take your data sets, give them to ChatGPT, and then ChatGPT will do the magic. It just doesn't work. They're not able to cope with that. It will give you an answer, but it's not the right answer. The problem is too complicated. So in everyday life, we talk about semantics and we trivialize the word. We say it's just semantics. So Steven Pinker, in his book, dates back, I think, over 10 years, maybe 12 years or so, a book called The Stuff of Thought. On the very first page, he talks about 9/11, so the events that happened on that day. And he says that I would like to explore a lesser known debate triggered by 9/11, exactly how many events took place in New York on the morning in September. Well, that morning in September. So as you may remember, there were the Twin Towers, 2 towers, a plane crashed into each tower. Okay, so why was this a question at the time? Because there was an insurance policy. And based on the insurance policy, if for every terrorist attack, for every event there was a terrorist attack, the insurance company would pay $3.5 billion. So the answer to that question, whether there was one event or 2 events, is actually worth $3.5 billion. So to make a long story short, they went to court and they decided that there were 2 events that day. Okay. So the owners of the Twin Towers got $7 billion instead of $3.5 billion. So how do we define the semantics? So we tend to say in common language, in everyday language, semantics is meaning and meaning is semantics, and we have this circular definition, and we go nowhere with it. The way that we define semantics is mainly through what we call mapping or reference. So we have the real world, we have things in the real world. We have a model like a blueprint. In the blueprint, we have symbols. You can have a rectangle in the blueprint representing a room in the building. So what does that rectangle as a symbol refer to in the real world? It refers to a real world room in a specific building. So this mapping between a model and the real world is semantics, or at least that's how we define semantics. And sometimes we tend to stress that this is real world semantics or material semantics as opposed to formal semantics in fields like logic and computer science. Okay, so we stress the emphasis on real world or material semantics. So in the work that we do, we always ask ourselves, what is this referring to in the real world? And to make things even more clear, I refer to a famous logician, Frege, I think 19th century logician. And he talks about sense and reference. So we know what reference is, and sense is about relationships between things. So if you look at the next picture, which actually comes from Chris's 1996 book, we have the planet Venus, and Venus is sometimes known as the morning star or the evening star, depending on whether you see it in the morning sky or the evening sky. So if we just have morning star as a symbol, and we ask ourselves, what does that represent? What does that map to? we would say Venus, and the same with the evening star. But that's quite a simplified interpretation of what's happening in reality. So if we unbundle the semantics of morning star and evening star, we notice that there's more going on and more objects involved in just one object. So there's the morning sky, there's Venus, there's the evening sky, and then there are two relationships between the morning sky and Venus and the evening sky and Venus. So actually, these relationships are first-class objects in the real world, or at least we consider them as first-class objects. So instead of mapping to just one object, Venus, when we say morning sky, it actually maps to three objects, because we have the sky, Venus, and the relationship between the two, and similarly with the evening sky. So the point here is that when we want to interpret data from a system, we need to unbundle its semantics. So its meaning in relation to what these symbols, these data, refer to in the real world. So if you look at this picture, some of you may see a face, some of you may see a vase, some of you may see something else, okay? And the point with this picture is that there's only one picture, but depending on your worldview, on your perspective, or the so-called paradigm from which you see different things. Okay, so that's the whole point. So if we interpret data of a system, depending on the perspective or the paradigm that we use, we will interpret the data in different ways, and we will carve reality in different ways. Okay? So paradigm is a term used by Thomas Kuhn in the Structured Scientific Revolutions. And just to give you an idea of what different paradigms that people may be familiar with, there's the evolutionary versus creationist paradigms, and then there's the Ptolemaic or geocentric paradigm versus the Copernican or heliocentric paradigm. So if you take the last one, there's one solar system. There aren't two solar systems, but depending on how you see it, the perspective, you can perceive it in different ways and interpret it in different ways. Okay? And it's a similar story with ontological representations. Depending on the underlying theories that you adopt, you will model reality in different ways. So ontology is a branch of philosophy and is defined by Lowe as a set of things whose existence is acknowledged by a particular theory or system of thought. Now, when we say a set of things, it's a set of things in the real world. So we can say, what is the ontology of this symposium? And we can start listing things that exist. Participants, presentations, speakers, tables, chairs, and so on. Now, the problem is that what I've just done is a subjective listing of things. It hasn't been done in any systematic or methodic way. So that's why we have the second part of the definition, which talks about particular theory or system of thought. So if we want to semantically analyze and interpret data in relation to the real world, what we need to do is adopt certain theories. We call them ontological theories, theories that tell us or describe how things exist in the world. And in this way, we can actually systematically and methodically come up with a model of the real world. So these theories are called metaphysical choices or metaphysical assumptions or meta-ontological choices. And they serve the purpose of carving reality in specific ways and also committing, and that's the word that ontologists use, ontological commitment, committing to what exists in the real world, especially top-level categories of things that exist in the real world. Okay. So why is this important for the practical purposes of information systems development and integration? Well, data represent real-world domains, so that's the problem space. We need a real-world grounding to interpret that data, and we get this real-world grounding from theories that derive from philosophy. Now, just to say that in disciplines like software engineering, knowledge engineering, data engineering, AI, if you like, all of those, mainstream, say, practitioners, researchers, I would say, don't really use any underlying theory to model what they do. Okay, and that's a big issue. And that's why we have all the problems historically over the decades of software systems not being effective. And today, that's why I think we also have issues with current AI systems, regardless of how amazing they actually are. Now, I'm not going to go through this. This is just an example of some theories or metaphysical choices that can underpin what we call an upper level or foundational ontology. I've highlighted in yellow the things that the theories that the ontology we use, which is BORO, the business object reference ontology developed by Chris many decades ago. So I'll say decades now. One that I'm going to focus on is the first one, a difference between endurantism, or seeing the world in a 3D perspective, and perdurantism, seeing the world in a 4D perspective. And I'm going to explain these in just a moment. Okay, so in philosophy, there are two schools of thought when it comes to change in existence. So one is endurantism, or for short, 3D. And this actually dates back to Aristotelian times when he described the substance paradigm, so it's very much related to that. And in this case, I'll explain it with an example. So in 3D, you see me now, and you're seeing the whole of me. It's all of me right now. In 5 minutes' time, you look at me again, and it's all of me again, okay? And the me now and the me in 5 minutes' time, or 5 minutes in the past, is the same me, okay? It's the same object. So you would say I'm wholly present at any specific point in time during my life, okay? And to answer the question of what preserves my identity, it's because I have certain properties, and a critique that can be made towards the 3D school of thought is that, well, we really don't know what these properties are. Some people talk about essential properties, and if you look at the Aristotelian substance paradigm, what they used to think is that there were these substances, things were made out of substances, and if you were to strip an object of all its properties, there would be some ghostly hulk, which would be the substance. And that would be actually the essence of the thing. So if I were to ask the question, if we have two people, John and Mary, why are they different things? The answer is that they have different properties, okay? It's the so-called Leibniz identity of discernibles principle. Now, if we look at 4D, which is the approach that we use, if you're looking at me now, you're not looking at the whole of me. It's just a part of me, more precisely a temporal part of me, because the whole of me goes from when I'm born to when I die. Okay? So in essence, if you consider the 4D universe and imagine being God living outside of space-time, you would be able to carve the space and time that I occupy. Okay? And that's the whole of me. Now, we can't really picture 4D in our minds. So the diagrams that I'm about to use actually have one spatial dimension and one temporal dimension to make things easy. Okay, so identity is defined by a thing's four-dimensional extension. Okay, and in this case, John and Mary are different because they have different spatial temporal extensions. So if you were to look at the universe from the outside, carve out the space-time that John occupies, carve out the space-time that Mary occupies, the different extensions, and they're different things, different people. Okay. So change here is explained via successive dissimilar temporal parts, and I'm going to explain it with an example. So this is just an example taken by philosopher Ted Sider. He explains it this way, where you have the dinosaur going from when it's small, when it's big, and the same with the human. So some people talk about temporal worms. So this elongated worm, which the object is in the 4D universe. Okay, so the example is about a company, and it's founded initially as a paper production company. And then at some point in its lifetime, it changes its activity and it produces electronics. So it goes from producing paper, so paper production company, to an electronics production company. And then ultimately it dissolves. So if we look at a 3D interpretation of this, and we use Euler diagrams here to look at the sets that exist. We have a set of companies, and we have two subsets, paper companies, electronic companies. And from time T1 to T2, Acme Limited is an instance of paper companies. And then at T2, we change its business activity, and it becomes an instance of electronics company. So as you can see, Acme becomes from being an instance of the subset paper companies, becomes then an instance of the subset Acme companies, electronics companies. Okay. Now what happens here is that the history of what went on, in a way, evaporates. Okay. If we were to implement a system in this way, we wouldn't keep track of the history of what went on. Now, one can argue we wouldn't implement a system in this way. We would always keep track of the history. But the problem is that if you do not use an ontological underpinning to design the system, then different designers, different modelers will do it in different ways. And if we do it in different ways, and we have to, at some stage, integrate the systems in the future, again, the operation would be very costly and time-consuming. Okay, so if we get things right from the start, that's what we think in principle, then interoperability will be less costly. So this is the example in 4D. So we have a space-time map. So as I said, to simplify, we don't have three spatial dimensions here, just one spatial dimension and then time. So this big rectangle represents the whole of Acme as a company. It starts with this incorporation, so there's a creation event. There's a change event when we change the business activity. And then there's a dissolution event when we dissolve the company. And in between T1 and T2, it's in a certain state or temporal part, which is paper production. Between T2 and T3, it's in another state or temporal part, which is electronics production. Okay, and here we can now see the whole history of it. And if we represent it with Euler diagrams and look at the sets that are involved, we have companies, and Acme always remains a company, obviously. And then we have company states. So we have state number 1, which is the paper production state of Acme. State number 2, which is the electronics production states of Acme. And then we have this relationship of temporal whole parts between the specific events and the whole of the company. So as you can see, these relationships are represented as tuples. We call them tuples, mathematical tuples. So Acme, which is the whole, has a temporal part, which is state number 1. Okay? This representation is immutable in the sense that we do not need to delete the history of what happens to the object. Okay, so this is a justification as to why you're using 4D. So it overcomes the traditional distinction between static and dynamic modeling. So if you take a field like software engineering, they make a big distinction between structure and behavior. And here the dichotomy ceases to exist. We adopt an upper level ontology, which is BORO. And the way that we do this over time is that we empirically, and by empirically, I mean that we look at the actual data of the systems and we derive generalized patterns. So by using these generalized patterns, we can save time in re-engineering systems in the future. Okay. And since it's an empirical approach, we continually test the models and the patterns. over different projects. And then we create a repository of reusable tested patterns. Now, I'll quickly go through this other example. I think I won't have time for the third example. And this is about processes. The reason I'm showing processes, because the previous one was about companies. So in traditional software engineering, we think of company as a static thing, okay? Not as a process. Whereas you've seen that we are considering that as a 4D object, so in a way as a process. This is a typical process, and it's a very simple example. It's about gardening. So we have a lawn mowing service, and here, this is how you would traditionally represent it in business process modeling. You have a series of activities. So here we have fueling the lawnmower, cutting the grass, cleaning the lawnmower, and clearing the lawn. And here we have a specific instance of Joe and John, the two gardeners, who go one day to somewhere and mow a specific lawn. So Joe, let's say, does the first half of the mowing. John then comes and does the second half of the mowing. Okay, so this is the example that we're going to look at. So this is our space-time diagram. What are the things involved in mowing that specific lawn? So there's Joe, John, the lawnmower, and lawn. So I'm not considering the fuel and other bits and pieces for simplicity. However, John and Joe, the lawnmower and the lawn, have existed before that specific activity and also afterwards. So what do we do? So the first activity is fueling the lawnmower. Okay, so what's involved is a temporal part of the lawnmower and a temporal part of Joe. Okay, so A and B represent that specific activity. Then we have cutting the grass. Okay, so what's involved during this period? The lawn, or the temporal part of the lawn, and the state of the lawn. The lawnmower, Joe, this part of Joe, and this temporal part of John. So this activity called cutting the grass is the yellow that you see. So it's all those things involved. And then we have cleaning the lawn. We have the lawnmower and John involved. And then clearing the lawn, where there's the lawn and John involved. So then if we ask the question, what is the actual process that we just carried out? It's this. So actually, it's what we call the fusion of all these temporal parts, of all those things that have taken part in mowing the lawn. So we are able to represent this in our diagrams and the way that we structure the data ultimately. So as you can see, we make no distinction between what's static and what's dynamic. Everything is 4D or extension. Okay, so these are some of the benefits which mirror what I've said previously. So you have a real world gap grounding, and if somebody uses this, or it's two different modelers use this approach, ideally what would happen is they come up with very similar models, very similar data structures, if you mirror this in an information system, so that we overcome that problem where if you take two different modelers or software designers, they will probably come up with three different models instead of one. Okay, I've spoken a bit about this earlier, so I'll just move on. And I won't go through this whole example, but just to show you through the diagrams that an apparently simple example, we start off with countries, becomes very complicated if we start asking the right questions. So this comes from a real project that we did many years ago, where we were re-engineering a financial system. All financial systems refer to countries, and this was the typical country table, country ID and country name. Now, the problem is that you have different classifications of countries, so you want to be able to overcome that problem, where you want to have both types of classification, where you have the United Kingdom with the home countries and so on. So these are questions that we've asked. Can the original system, can the legacy system answer these questions? So Can a country instantiate multiple classifications? And the answer was no. Can multiple country classification systems be represented? So can you have an ISO representation of countries, a Bank of England representation of countries, and even our own classification of countries? The answer was no with the legacy data. Can both nesting, like the United Kingdom, and nested countries, the home countries, be represented? And the answer was no. So then, again, I won't go into detail. We went through a series of steps, and what happened is that ultimately we ended up with a final model, which looks something like this. And thanks to this re-engineering process, using a 4D approach, we ended up answering all the questions, all the requirements that we couldn't be answered previously. And then going back to Thomas Kuhn, who looked at scientific theories, and he came up with dimensions of improvements for scientific theories. We've applied these dimensions to the work that we do. So just to look at one, so objectivity, the new model is not dependent on a specific system implementation of an organization's perspective, since multiple classifications of countries are now possible within the same enterprise system. Okay? So the new solution is more objective, more general, more precise in the sense that it's more accurate, reflects the real world, explanatory power in the sense that it can cope with, it can explain more about countries, simplicity and precision. Okay? So those are all the dimensions of semantic improvement that you would have to define afterwards once you carried out the re-engineering project. Okay, finally some conclusions. So one thing that I like to point out, because I know I'm running out of time, is that this is becoming more mainstream. So 4D ontology is becoming more mainstream. There is a government standard, and the new version of this government standard, Information Exchange Standard, IES, has now an upper ontology, which is grounded in 4D. Okay, so government seems to be adopting this type of modeling approach. And I think what is also crucial, one more thing, is that there aren't many experts in this. So the problem we have now is that those few experts that exist, okay, well, we're kind of getting older, so we need to actually educate the next generation. So that's it. Thank you very much. And